All right, guys. So we'll get started. Next homework is due Tuesday. Okay, so a little bit less than a week from now. For this week's lab, we are going to use the Pascal software again. So if you have deleted from your laptop, you can install it before you come into the class. Okay, so that will save you some time. Um, for the in-seat classroom disinfection, I'm asking Abigail and Sarah for that after class. Okay. Um, for your exam number 2, most of you guys have taken the exam already, but there's a couple of you guys who are either sick or had to be in quarantine. So in that case, not all of the class has taken exam 2. Okay, so but if you have taken it, I have your grade already put in Moodle for your exam number 2, and then in the feedback of your exam number 2, I put your current grade of the class. Okay, so you may want to refer to that. This Friday is the last day. If you decide want to either keep or withdraw the class. Okay, so that might be a piece of information you want to look into. Okay, all right. So today we'll be still looking at magnetism here. On exam number 2, let me just make one more comment here. So most of, or not most, but many of you guys may be feeling that you were not doing well on exam number 2. Okay, so this is the nature of this class for exam number 2. Typically, the class as a whole is not doing well on this exam because this is I would say the most difficult content of the class. Okay, and then for the next exam, it's slightly easier, but not much easier than this one. Okay, and then the last one will be easier. Okay, so the first again is considered to be easy. The second one is the most difficult, and then the third one will be still difficult, but the last one will be easy. Okay, so um, now you probably learn that if you just study the day before the exam, that would not work out very, very well. Okay, so again, I just want to remind you guys for physics class, you want to spend your effort throughout the semester, not just a few days or the day before the exam. Okay, that would probably will not work out well as you expected. Okay, all right. So um, let's take a look on what we learned last time. So last time we take a look at magnets. Okay, so this is similar to charged particles, but for magnets, each piece of magnets have 2 poles. Okay, the south pole and north pole, and similar to the charges, like poles will repel each other, and then the opposite poles will attract each other. Okay. However, if you divide magnets into small pieces, then each piece will have a south pole and a north pole. Okay, so that's for every piece of the magnets, no matter how small it is. For charges, if you divide the charge into small pieces, then you pretty much like make them like smaller in the amount. Okay. All right. So the Earth itself is a giant magnet. It has its north pole that is close to the south pole of the Earth geographically. Okay, about the same, but a couple hundred miles difference there. Okay. So for magnets, the material that has magnets, that's because um, they are the electrons inside an atom. Each electron will create a magnetic field due to the movement of the charge. Okay, and if these atoms can line up, so then you will have the magnetic field, total magnetic field. Okay, often cases, each atoms are randomly orientated, so then the net magnetic field will cancel out. Okay, as a result. All right. So for the material that has the tendency to align with each other of their atoms, they are called ferromagnetic materials. Okay. only iron, cobalt, nickel, and gadolinium, they are ferromagnetic materials. Okay. For other materials, if you have external magnetic field in the area, then it can also be magnetized. So that means the domains inside will be lined up with the external magnetic field. However, if you remove the external magnetic field, then the orientation, the alignment of domains will disappear. Okay, so then become random again. So loses the magnetic field. Okay. For ferromagnets, if you heat the material above 770 degrees Celsius, then you lose the magnetic field. Okay, so then the domains inside will be random because of the thermal effect. This temperature is called the Curie temperature. Okay. All right. So the origin of the magnetic field is the movement of the charge or the current. Okay. So once you have current, then surrounding that current, you will generate a magnetic field. Okay. The for an electron inside atom, it's orbiting the nucleus, so then it creates a magnetic field. Okay. So like that, it's because this is a current, because this is a charge actually is moving, so that produce the current. Okay, so in that case, we use magnetic field lines to visualize the magnetic fields, just like we do for the electric field. Okay, so for magnetic field lines, they are continuous. They are a closed line for each of the magnetic field lines, so it's continuous and then closed lines. Any two of these magnetic field lines, they do not cross. Okay, so that means field is unique at any point. The line densities represent again the strength of the field, just like the electric field line. Okay, when you have a charge that is moving inside a magnetic field, then it will experience magnetic force F. F is given as the magnitude of it is the charge magnitude of the charge times the speed of the charge times the magnetic field B times sine of theta, where theta is the angle between the velocity and then the magnetic field. Okay. The direction of this magnetic force, you will use the right hand rule number 1. So your thumb goes in the direction of the velocity, and then the magnetic field are along the direction of the fingers. Then your palm is facing in the direction of the magnetic force F, okay, for a positive charge. If you have a negative charge, then the force will be in the opposite direction, okay? So in the opposite direction your palm is facing, that will be your direction of the magnetic force on that charge, okay? And in this case, you can see force is always perpendicular to the velocity and then also perpendicular to the magnetic field, okay? That would be the magnitude, and then the direction will be in that direction. And we also talk about the force on a moving charge in a magnetic field. So unlike when you have a charge moving in an electric field where the motion or the charge will be deflected, in this case, if you enter the field with V velocity and B field initially perpendicular to each other, then you'll have a circular motion, okay? Because the force is perpendicular to the velocity, so then it only changes the direction of the velocity. Applications of this is you can have a velocity selector for charged particles. Okay, so only given velocities of charged particles will pass through that region. Okay, so that you can determine what will be the velocity of your particle there. And the other application is the mass spectrometer. So where you have the presence of the magnetic field, so then this is having circular motion. Okay, so the radius of it can be determined for this circular motion can be determined by where the magnetic force is the centripetal force. Okay, starting from there, it gives you mv over qb. All right, so for different isotopics, they pretty much have the same charge but different mass. In that case, the heavier the mass, we will have heavier the or larger the radius. Okay, so that's the working principle of mass spectrometer. All right, and then we were about to take a look on this example here before we run out of time. So let's take a look on this one. It says find the radius of the orbit when an electron or a proton moves perpendicular to a magnetic field of 0.86 Tesla with a speed of 6.47 times 10 to the fifth. Okay. So if you have an electron or proton moves perpendicular to a magnetic field, okay, so you can that's what the figure show in the previous a couple slides back. Okay, so when you have V perpendicular to B to start with, then the charged particle will have circular motion in the presence of the electric magnetic field. Okay, so let's say that's the circular motion. Okay, and so in that case, the magnetic force F equal to QVB sine of theta. In this case, because this is perpendicular to each other, so sine of theta is 90 degree. So then sine of theta will be 1. Okay, so if you take sine of theta there, this is 1. Okay, so just QVB, and it will have a circular motion. So then centripetal force is equal to that guy. Okay, so mv squared over r is equal to that guy. Those two are the same forces. So QVB equals to mv squared over r. You are looking for the r, the radius of the orbit. Okay, v and v will cancel out again. So this is the equation we had in the previous slide. Will be equal to mv over qb. Okay. In the problem, it tells you the B field and the V, the speed. Okay. And you also know the mass and the charge. Okay, for electron and a proton. So those are the hidden information, but when you see a proton, you immediately realize that the electron is given, the charge is given, and then also the mass is given. Okay. So then for electron, R is equal to the mass of electron times the speed given divided by the charge of electron should be E times the B field, the magnetic field. Okay. And you put in the numbers for electron. This is a constant number you can look up if you don't remember. Okay. So 9.11 times the speed 6.47 times 10 to the fifth meters per second over 1.6 times 10 to the negative 19. Again, this is a constant number. You can look up if you don't remember it. 0.86, that's the magnetic field. Okay. So in that case, that gives you 4.28 times 10 to the minus 6. All right, that's the radius of the electron orbit. Okay. On the other hand, if you have a proton that is moving in the field, then the mass is a different mass, P, which is the mass of the proton, the same speed. E will be the same. Okay, so for proton carries the same amount of charge as the electron, but positive. Okay, but we are just looking on the radius. Okay, so we do not have to care about the sign of the charge there. For this m mass of proton, it's again a constant number that you can look up. speed is the same speed there, divided by 1.6 times 10 to the minus 19 again, 0.86 Tesla there. Okay. So this would be about 7.87 times 10 to the minus 3 in meters. Okay. So you can see for a proton and for a electron, they have different radius. All right. Any questions you guys might have? Just let me know if you are online. Just unmute yourself and speak up. Okay. All right. So if you are clear, I think we can move on here onto the next section on cause of effect. Okay, so it was discovered by Edwin Hall in the late 1800s that if you have a conductor inside in the presence of the magnetic field in this case, okay, so and the charge carriers inside the conductor will experience the magnetic force because there's magnetic field here, and then the Q, the charged particles are moving there. So then there will be this magnetic force F, okay? In the case if you have positive charge carriers of the conductor, okay? So most conductors we are dealing with are metals. In that case, electrons are the charge carrier, so that will be electron. But some conductors, especially some semiconductors, the charge carriers are positive charges, okay? So then due to the magnetic force, so then the charge will be dragged, deflected onto the top of the conductor in this case, okay? So then you have positive charge build up on the top here, then there will be negative charge over there, okay? And because of that, because now you have charge accumulation on this side, and then the opposite charge accumulation on the other side. So then there will be electric field building up as the result, okay? The result will be for, if this is positive charge, you can see positive charge will be built up there. And then, so then there will be electric force on this guy, which will be pulling it downward, okay? As you build up the charges on the two sides of the conductor, electric field will be large enough to balance out the magnetic field, okay? So when that happens, then the charge will be no longer deflect upward. It will be just go through, okay, after that, okay? So you can actually measure what's the electric field, the potential field, potential build up by using a multimeter like this, okay? So just connect to the two sides of the conductor there, and then you can see it will reach to a maximum point, then will not increase anymore, okay? You'll start with 0, but as charge builds up, it will increase, and then it will reach to an equilibrium value there, okay? So in this sense, according to the signs of the voltage you are measuring, you can determine what will be the charge carrier of the conductor. Either it's a positive charge carrier or it's negative charge carrier, okay? Just looking at the signs of the voltage here, so you can determine which side will be having positive charge, which side will be having negative charge, okay? And then if you know the external field, the magnetic field direction, you will be able to tell that, okay? And so this is the voltage measured, called V sub Hall, sub H, that means due to Hall effect. That should be equal to the electric field build up times the width of the conductor, okay? That's equal to, so the electric force is equal to the magnetic force. So this is the, yeah, VBW. All right. So yeah, there's derivation, a little bit derivation here. So E Q times this guy. Okay, so Q times E should be equal to Q VD or V QVB. Okay, QE should be equal to QVB. So then Q and Q cancel out. So then E is equal to V times B. Or if you do E times W, which gives you H, the V, the voltage, should be equal to VDW. Okay, so in that case, V measure should be equal to the speed. So this is the speed of the charge carrier. Okay, times the B field times the width. Okay, so if you can measure the voltage, you can calculate the drift velocity of the charge carriers. Okay, or if you know this guy, you can calculate the magnetic field. So the other way around. Okay, but basically the voltage built up is equal to the velocity of the charge times the magnetic field and times the width of it. Okay. All right. So that's basically how affect. So next section here talks about the magnetic force on a current carrying conductor. Okay, so for example, if you have a wire that carries current, okay. Now, if you look into the microscopic view of the wire, if it carries current, so that means there's charge moving inside the wire or inside the conductor. Okay, so we know that for each individual charge that is moving in the presence of the magnetic field, there will be a magnetic force. Okay, so then for a current carrying wire, so there will be a collectively force, magnetic force on the wire due to, for each charge here will experience magnetic force. Okay, so that's where this magnetic force on a current carrying conductor is coming from. That is given as the current times the length of the wire times the magnetic field times the sine of theta. In this case, theta is the direction of the current mixed with the direction of the magnetic field. Okay, so theta is between B field and the current I. Okay, and this result actually is a cross product of the two vectors. The current vector cross the magnetic field vector. Okay, so I think we don't have to know the vectors product in this class, but if you have learned that somewhere, you can apply it here. Okay, but basically this is what it gives. Okay, F magnitude is the current times the length of wire times the magnetic field times sine of theta. Okay. All right, so let's take a look on one example here. This one says the long thin wire shown in the figure is in a region of constant magnetic field B. The wire carries a current of 6.2 amps and is oriented at an angle of 7.5 degree to the direction of the magnetic field. If the magnetic field, if the magnetic force exerted on this wire per meter is 0.038 newtons, what's the magnitude of the magnetic field? Okay. And then in part B, it says at what angle will the force exerted on this guy per meter be equal to another number? Okay, so basically, if the angle is different, force magnitude of force will change. Okay. So on this one, the equation you'll be using would be this equation of the force on a current carrying wire is equal to I, the current times the length of it, times the B field times sine of theta. Okay. So you guys can give it a try, and then we can take a look at the solution together in a couple minutes here. right, so I think we can take a look at this together here. So it tells us that the current is 6.2 amps. Okay, so we know the current, and then it tells us the angle. All right, we're looking for the magnetic field B, and it also tells us the magnetic force per meter is 0.038. So that means F over L, this is force per length, okay, is 0.038 newtons. And then I is given 6.2 amps. The angle is given as 7.5 degrees, right? So you can see in this case, then you can rearrange this equation. So you can write it as F over L equals to I times B times sine theta. So then you have this on the left, you have I and sine theta, then B can be solved, okay? So you can rearrange that. So your B field will be equal to F over L, okay, divided by I sine theta, okay, in that case. F over L is 0.038 newtons per meter, okay, that should be per meter there, over the current 6.2 amps times sine of 7.5 degrees, okay. So if you put everything into your calculator, this will give you 0.047 Tesla as the strength of your magnetic field, okay. Now B is basically asking you if the force per meter is changed, then what will be this new angle? So basically, if you change the angle, you'll change the force or force per meter, okay, so either way. So in that case, you can still use that equation over there, F over L equals to I B sine theta. Now you'll use the B here that you figure out there, and then this is 0.016 newtons over meter now on the left equals to the 6.2 amps times 0.047 T sine of theta, okay, and then you solve for your theta. So then sine of theta is equal to 0.016 newtons over meters over 6.2 amps times 0.047 Tesla equals to your sine of theta, okay? And then you do inverse of that. I think I forgot to do that on my note, but you guys should be able to do this. Okay, so 0. Let me see what will be the answer here. 0.016 divided by 6.2 and then divide by 0.047. That gives you 0.0549 on this side equal to sine of theta. And then you do inverse of sine of that, okay, to get your angle theta. And we can express this in the degrees. So theta is equal to 3.15 degrees, okay, roughly, on that guy. Any questions you guys might have? All right, so if you are clear, we can move on here. So if you have a wire inside the electric field or magnetic field, then there will be the magnetic force, okay? So However, if you have a loop that carries current, okay, so like scenario like this, if you have a rectangular loop like this, so if there's current inside it, then the whole thing here will experience forces on each side, okay. Now, in this scenario, if this loop is in the same plane of the B field here, so that means this is parallel to this guy. So then the theta is equal to 0 for the force, F equal to ILB sine theta. So this guy, the force on this guy will be 0, and then on the bottom here will be also equal to 0, because at the bottom here the theta is 180 degrees, sine of 180 is also 0. Now on this side, okay, the force, so the current will be going down here. The B field is in that direction, so you can use your right hand rule. So your thumb goes in the direction of the current, going down, and your four fingers goes in the direction of the magnetic field. So you basically place your right hand like that. So then power is facing out, okay, on the right part of the loop here. And then on the other part, because current is going upward, so then the force is in that direction. So you can see one force is pulling in this way out of ball. The other force is pushing it into the ball. So then overall, you'll have a overall torque of making this loop rotate with the center axis, okay? So how much of that torque in the figure shown, you can calculate. So I times L times B, okay, that will be the magnetic force on one side, on the left-hand side or right-hand side, either way, times the distance to the rotational axis, okay, that gives the torque. Force times R gives you torque. Then this is on the other side, okay? So then the two add up to should be I times B times H, okay, and then times W. You can put H times W together, which gives you the area of the rectangular shape, okay? So the height of it and then the width of it gives you the area, all right? So then the torque on that loop will be equal to I, the current, times the area of the loop, times the B field, the magnetic field, okay? So that's what we have. Now, although we took a look on the rectangular shape, but this can be applied to other shapes as well. As long as you have a loop, then torque is equal to I times A times B if the loop is in the same plane of the that is parallel to the electric field or the magnetic field, okay? However, in general, your loop might be having an angle, okay, with the magnetic field. So in this case, the loop has an angle with the magnetic field, okay? So let's take a look on this one. This is a top view of the loop we saw earlier. So in this case, you can see the normal direction and then the B field, the more normal direction of the loop and the B field, they are perpendicular to each other, okay? So then if you do sine of that 90 degree, that would be 1. So in the general expression for a loop of area A that is in the magnetic field, so torque should be equal to I times A times B times sine of theta, okay? So this is the scenario we had. In general, theta might not be equal to 90 degree, it could be any angle. So theta is the angle between the normal direction of the loop and the magnetic field B, okay? So the theta is the angle of the normal direction of loop makes with the the magnetic field B, okay? All right, so that gives you that equation there, I times area, current times area times magnetic field times sine of theta, okay? In reality, for the design of a scenario like this, you have probably like multiple loops stacking together, okay? Let's actually design for a motor or a electric generator, okay? So those are the two major applications of this. But in those two scenarios, you have like n turns of identical loops stacking together and then in the presence of the magnetic field, okay? So if that's the case, if you have n numbers of loops, then the total torque is equal to number of loops n at the bottom line here, the last equation, times the current times the area and times the magnetic field times the sine of theta. Again, theta is the angle between the normal direction of the loop and the magnetic field B. All right. Any questions you guys might have before we move on to the next section? All right. So the next section is about Ampere's law. So this could be an analog to the Gauss's law we learned earlier. Okay. So for Ampere's law, it relates to the current through a surface, okay, of a closed path, right, and then to the magnetic field. So basically, if you have a closed path like this, okay, and if it encloses like two currents over here, so then the B field along the direction of the loop of the path here, okay, so B in that direction times delta L, okay, in the tangent direction times delta L. If you sum that up, okay, it will give you mu naught times I enclosed, where mu naught is the a constant number. It's called the permittivity of free space. All right. So mu naught equal to 4 pi times 10 to the minus 7 T in Tesla times meter over amps. Okay. All right. So in this case, if you have a circular loop like this, then the B times the whole length, the 2 pi r, is equal to mu naught times I enclosed. Okay. All right. So in that case, then Ampere's law can be used to find. So for a long wire that carries current I, if you take a path, closed path that is radius of r, and then use the so this direction for the direction of the magnetic field is determined by right hand rule. Okay, so number 2, so this is to determine the direction of the magnetic field. In this case, you put your thumb in the direction of the current and then 4 fingers curls in the direction of the magnetic field. Okay, so your magnetic field goes in this direction there. So apply Ampere's law, you do B field times the length of the closed path, which is the circumference of this circle, 2 pi r times B equals to mu naught times I. So then B field is equal to mu naught times I divided by 2 pi r. Okay, so that gives you the magnetic field for a long straight wire. All right, I think we have a couple examples here. So the first one here, it says find the magnetic field 7.25 centimeters away from a long straight wire that carries the current 6.81. So this one could be straightforward. You can just apply the equation we learned for the magnetic field for a long wire. Okay, so this would be just this equation B equals to mu naught I over 2 pi r. Okay, in this case, it tells you R is 7.25 centimeter and then I is equal to 6.81 amps. Okay, mu naught is the constant of 4 pi times 10 to the minus 7. All right, so let's take a look here. So you would just plug in the numbers. Mu naught is 4 pi times 10 to the minus 7 Tesla times meters over A. Current is 6.81 A, okay, divided by 2 pi times R. This is in centimeters, so you convert it into meters. All right. So before you plug in the numbers, you can take a look here. So there's 4 pi and 2 pi. So we will partially cancel out. You will have 2 on top, and then 2 pi goes away at the bottom. Okay, so then you can plug in the numbers there afterward. So this will give you 1.88 times 10 to the minus 5 in Tesla. Okay, that will be your magnetic field produced by this wire. Right. So let me know if you have any questions about this one. If not, we'll take a look on a second example here. This one says 2 long straight wires are orientated perpendicular to the page. As shown in the figure, the current in one wire is 3.0 amps pointing into the page, okay? So this guy I1 with a cross, that means goes into the paper. That's the back of the arrow. And then this is the head of the arrow, goes out of the paper. That's the second current, 4.0. So you have to imagine this is the long wire going into the paper, and then out of the other one goes out of the paper. Okay. It says find the magnitude and direction of the net magnetic field at point P over here. Okay. So what will be the net magnetic field over there? Okay. So a dot means out of paper, out of page. A cross means into the page. Okay. So this is a square with a side of 5.0 centimeters. Tells you to use X and Y like this. Okay. You're looking for B field at this point. All right. So we can take a look on this one together. Um, so you have two wires carries current. So then there will be so magnetic field at this point, okay, should be as a result of the two magnetic field add up, one by this wire one and then one by this wire two. Okay, so this current is going into the paper, so you can put your right hand, your thumb goes in that direction into the paper, and then you curl your forefinger. So in that way, so you will figure out that then the magnetic field produced by this wire at this point B will be in this direction, okay? In the direction of your four fingers at that particular point. By this wire, the second wire is pointing out of paper, so you put your thumb out of paper like that, and then your forefinger curls around like that, okay? So it will then be in this direction because this is the R direction, okay? At that direction, perpendicular to R, but in that direction, okay? So that will be your magnetic field produced by this guy, the second one, okay? The second wire. Then the total magnetic field should be unique, or should be a combination of the two, okay? It's kind of in this direction somewhere, okay? That will be, or maybe here, somewhere here, okay, up to this point, okay? So that will be your total B field, okay? So you probably realize then this is addition of two vectors, B1 and B2. So for the total B field, magnetic field, B total should be equal to B1 plus B2, okay? And then to do the vectors addition, we need to do the X and Y direction, okay? For B1, it looks like it's going to be just having the X component. For B2, it looks like it will have two components, X and Y, okay? So B of X should be equal to B1X plus B2X, okay, for vector addition. And then similarly for by, y direction, y component of B field is equal to B1y plus B2y, okay? So let's do the X component first. For the magnitude of B1, it's going to be the mu naught times I over 2 pi r, okay? So it'll be I1, R1. R1 will be this guy, okay? And then this will be R2, the diagonal line, okay? So let's see here. So B1 is purely just the X component, okay? So then B1X will be just equal to B1, okay? So it will be the mu naught I1 2 pi R1 plus B2, okay, the magnitude of B2 should be equal to mu naught I2 over 2 pi R2, okay? So R1 will be equal to the side of the square. R2 is the diagonal line, should be square root of 2 of A, okay? If this is a square, then it's square root of 2 because it will be A squared plus A squared and then take a square root, okay? So then in this case, we can write this as A instead of R1 because R1 is equal to A there, plus B2. For the X component, it should be in this way, right? This is B2X, okay? And we should know that this is a 45-degree angle because this is 45 over here, all right? And then this is perpendicular to that, so this is also 45, so that's also 45, okay? If this is 45, this is a right angle, this is also 45, okay? So plus B2 for this guy, if this is 45, then the X component will be negative, right? Because this is negative X direction, okay? So let's do mu naught I2 now, 2 pi for R2 is square root 2 of A, okay? And then cosine of, so negative cosine of 45 degree, okay? For that X component. All right. And then you basically plug in the numbers over here. Okay. Yeah, so you can do the mu naught over 2 pi a. Those are the common factors. Okay. And then you will have I1 from the first one minus cosine. So it'll be minus of cosine of that guy will be, there's this first one here, I2 over square root 2 times cosine of that one will be 1 over square root 2. Okay, cosine is 1 over square root 2. Okay, so then it becomes 1/2. Okay, so you can plug in the numbers now. 4 pi times 10 to the minus 7 Tesla meters over A over 2 pi times the 5 centimeters, 0.05 meters. I1 is 3 amps minus I2 is 4 amps, but divided by 2. Okay. So this will give you 4.0 times 10 to the minus 6 Tesla. Okay, that's your X component. You can do the Y component. Y component will be purely coming from B2 because B1 is in the X direction purely. Okay, so it'll be equal to B2 of Y. And that will be again just mu naught I2 2 pi R2 would be square root 2 of A times, it's in the downward direction, so negative of 45 degrees. Okay, so you can put in the plug in your numbers now, times 4.0 amps 2 pi square root of 2 times 0.05 meters times negative of, again, square root of 1 over square root of 2, that's sine of 45. Okay, so that's minus 8.0 times 10 to the minus 6 Tesla. This is your Y component. All right, so then the total magnitude will be square root of X component plus Y component. Okay, you can plug in the numbers. So X squared plus Y squared, I will skip that. It will give you 8.9 times 10 to the minus 6 Tesla for the magnitude. And for the directional angle should be tangent inverse of by over bx. Okay, so plug in the numbers, you got y over x, that gives you negative of 63 degree of angles. Okay, all right, so this is again a vector addition. All right, any questions you guys might have? Okay, so if not, then we'll stop here and then come back on Friday.